serves as temperature regulator as well as the humidity regulator in both conditions. Thereby, if you have a graph between, this is loss of water happening. Now, if I want to measure a different relationship between, I want to determine the relationship between the loss of water that is happening. This is kg per meter square of the surface with respect to the RH value, that is the relative humidity. RH is measured in percentage. So you would get a graph like this. So near 80% RH value, you would get the minimum amount of loss of water, and at around 20%, you could get around the highest amount of loss of water that is happening. So if this is on the normalized scale, I'm just measuring on the normalized scale where 1 is the ultimate factor. So this means normalized means it's around normalized over some different percentage, different values. So you have, then what do we know now? That loss of water is actually decreasing with the increase in RH value, with the increase in the humidity value. Next, if we measure RH, the relationship between loss of water, this is loss of water again in the same units, kg per meter square, with respect to air temperature outside as well as concrete temperature. Let's say that the temperatures right now are close enough near the surface, temperature in degrees Celsius. So you will find out with increase in the temperature, there will be an exponential increase in the loss of water. So at 30 degrees Celsius of the air temperature and the surface concrete temperature, the loss of water will be almost 80% of the maximum that it could happen. And this is just at 20 degrees Celsius. The loss of water is just 20% of the maximum. And still at 10 degrees Celsius, it is still the same. So there is hardly any difference here between 10 and 20 degrees Celsius. So the ideal temperature always for concreting as well as for curing is 10 to 20 degrees Celsius. And 15 degrees Celsius, which is the room temperature, always considered to be the ideal temperature for concreting. Now, I told you that the curing depends on the size of the assembly. So it's actually dependent on the actual loss of water that is happening, and the actual loss of water is dependent on the relationship between surface to volume ratio of any assembly. So if the surface area is more, there will be more loss of water. If surface area with respect to the volume is less, so lesser this ratio, lesser will be the loss of water. Greater this ratio, surface to volume ratio, more the surface area, more will be the loss of water through evaporation. So the surfaces should ideally have less surface area, but you cannot avoid that. For example, in slab, that's why in slabs there is maximum amount of curing done for slabs, because the surface is more with respect to the volume. It is more like a surface element and like an area element rather than a volume element. The surface area of the slab is quite large with respect to its volume. So that's why there is a large loss of water in slab, and that's why we cure the slabs much more than any other material, any other element within the structure. So what else? The loss of water leads to loss in strength of concrete. Now, if there is a loss of water, there will be a loss in the uh, hydration. There will be a decrease in the hydration rate, and thereby the strength of the concrete will decrease. So it has been observed that a relationship between strength, compressive strength, and if I take the relationship between compressive strength with respect to age of concrete in days, this is age of concrete in days. So you would get a graph like this if it is, and like this if this is totally immersed in water. So it's continuous curing. And if this is completely kept dry, no curing done after the initial stage of after the concrete has been cast. So if it's completely immersed in water, this will be the happening. So even at 180 days, yeah, this would be the behavior at 180 days. This is at 90 days. This is at 28 days. So you will find out that keeping immersed in water is actually leading to increase in the compressive strength. By how much? It has been observed. This is from a research, 40 megapascal here, and completely dry. This is just 25 megapascals, just 15 megapascals. So there is around 120% increase, 130% increase in the compressive strength when it's completely immersed in water once hardened, once final setting has been undertaken, and compare that with when keeping it completely dry. So keeping it completely dry would mean no this much loss in compressive strength from what it could actually gain for the same amount of material. So curing then becomes a very important thing for concrete. And we now if we are completely immersing it in water, अगर हम पूरा इसको water में immerse कर रहे हैं over a period of time, so we have curing tanks in our labs. These are curing tanks. What is done in curing tanks is that the concrete sample is placed, which is a cube sample, it's placed in water for a period of 7 days at least. At least for 7 days, it's kept there. While testing it, you can, if you want to know the overall compressive strength, you can go for 28 days curing of the samples within the curing tank. Now in curing tank, you have water here, and the sample is placed within that water. Now, to those whom I showed the curing tank, once we were visiting the lab, there were two curing tanks we are developing in the new lab, and I showed you that the one of the curing tank would have the temperature control. So what we plan to do there is that we plan to put in heaters with auto sets such that once the temperature rises about 30 degrees Celsius, they will be shut down. So you will have a auto stop to those heaters once the temperature of the water rises about 30. So we'll be having controlled research on the effects of curing at around 30 degrees Celsius on the, so we could even increase the temperature of the water beyond that if we want to do the research for the research purposes, we can keep on changing the temperature of water and know the effect for prolonged overheating and underheating of the water due to the curing water. So 100% of RH is maintained in a curing tank because there is always water around it. So RH values are always around 100%. I can show you the figures. Those that who did not visit the labs and others. So there are mechanical curing tanks, and you can just make manual curing tanks. So this is a mechanical curing tank. You can just make it with steel, mild steel, or stainless steel if you want to avoid the corrosion of the steel. And there is a regulator, a heater installed here. So curing tanks of different shapes and sizes can be made of steel with regulation of the temperature for study in the labs for at controlled temperature as well as humidity. Even at your homes, you can have just a simple container acting as a curing tank for testing the samples. And there is always you must have seen the element that you put within the water for temperature regulation. Even in the steamers that we use in our homes, wherein we put in the temperature, this element, and that heats up the water. So you can check the temperature at different times, and this setup can easily be made even at your homes for testing of concrete samples, the behavior of the concrete samples. But this, and it will cost very less because you can make it even of plastic. So this is about the curing of concrete. So what was the purpose of curing of concrete through wet processes? Was to the wet processes that we discussed, it was to keep the concrete in moist climate always. But the other one, which is the membrane curing, this is a reverse process. In this process, you actually prevent the water loss from concrete. How do you prevent the water loss? By providing a membrane between the concrete and the atmosphere. So you will provide a membrane between the two, and this is concrete, and there is atmosphere all around it. So you actually try to prevent that by providing a membrane around it. So this membrane prevents the water from going into the atmosphere. Now, this membrane could be of different materials. You could have they may be plastic-based materials. Now, in plastic-based materials, for example, you have the polythene. Even if you put polythene over the concrete surface, it will prevent the evaporation because it will act as a barrier between the concrete and the atmosphere for direct evaporation happening from there. But the evaporation particles may still be there. They will be collected underneath the surface of the polythene. So that will keep the undersurface moist even when the evaporation may be happening due to heat, but that will be collected on the polythene and that will be available for recuring of the this concrete sample. So that's the polythene sheeting that you could go for. You could have reinforced paper is a material that is used for membrane proofing. Then you have paper with white surfaces. White surfaces because it's actually reflecting the sunlight, so it's aiding in less evaporation happening from the surface. You could have wax emulsions being applied over the surface, so it's preventing the curing, uh, the evaporation from happening from the loss of water. You have the acrylic surfaces, surface coatings like you have in the paints, and that prevents the evaporation from happening. So if you apply the acrylic surface coatings, which may be styrene based coatings, or you could even use chlorinated rubber. For so I showed you how the curing tanks are made, but do we go for testing of the curing compounds? Yes, we can even go for testing of all these compounds. But and how do we measure? We measure the curing efficiency, and curing efficiency is a term which is used to measure how much curing is effective for concrete. So it's actually related with the strength of the concrete. So there is it's actually a qualitative means of determining the efficiency of the curing by relating it with how much strength is actually being achieved during the process of the curing. So curing, you can have continuous or intermittent. You could have continuous curing or intermittent curing. Now, continuous curing is keeping it completely moist over a period of time. Intermittent we usually do. हम सुबह उठ के we apply the water through the pipes onto the surfaces. शाम को फिर से apply करते हैं. So during the daytime, it's not being cured, although some amount of moisture on the surface will be available. So you will always get less efficiency in intermittent curing, but it is like that. You need to have concreting with an optimum amount of strength that you need to develop. So even in intermittent curing, you could achieve extra 70% of the strength that you want to achieve. But in continuous curing, you could achieve even 120% of the strength of the initial strength that it has. So continuous curing would always be good in all weathers, in all climates, but it is not possible at site in large structures to cure it completely at all times. And it also involves in costs. In our homes, we construct column structures, and we do not provide the gunny bags. It involves cost. Actually, the cost effect is very less. A gunny bag would cost 50-60 rupees, and even around 100 gunny bags would be a 5,000 rupees to the cost of the construction that we usually meet, which is around in lakhs. So keeping a 100 bag gunny bag at our homes, which is 5,000 rupees, is not a huge cost. But still, we do not focus on curing because people do not have knowledge about how important is curing and the length of the curing. How important is the length or the time of curing? So the length and time of curing is very important. So that will be actually decided by different seasons. It has been observed that once the strength comparison was made in different seasons, it is seen सबसे कम strength concreting की that comes in if this is Jan and this is December, this is July. The minimum strength is in Jan, The maximum strength is in July, and December again it goes near to what it's in Jan. So minimum strength would always be achieved in Jan. So that's due to the temperature drop. And then our uh, this focus on that curing is not required in cold climates. So we do not apply the water during the cold climate. So we it has been always seen that in July in the northern hemisphere you are getting the maximum amount of strength, maximum strength here. This is strength versus, and then what it has been observed. I checked one more graph that is strength in comparison to different years. This is strength in comparison to different years. You will see that in I checked this for 1970s to 1990s first. It has been seen that years around 1980s, the strength achieved was highest, and it again decreased towards 1990s. Now, on what factors did it depend that the strength achieved during these years in concrete was higher as compared to in 1970s and 1990s? And once it crosses 1990s, what is the effect? There has been no further studies, and I could not get any further studies on this. I tried to check. So around 2000 and then 2010 and up till 2020, what is the effect? Is it due to only climate? It has been observed that the strength has increased since 2000 due to advanced technology in manufacturing of cement. That is due to advanced technology in manufacturing of cement, wherein we are getting much finer cement now. So the strength of concrete has definitely increased since year 2000, but this was observed over different climates for the same nature of the cement. So, but there has been no study on the same nature of the cement for different climates and different years. So there was something in 1980s with the climate of the world, which led to higher. This led to higher strength during those years. So it must have been something to do even with the temperature of setting as well as temperature of curing.